NENOMATICA, where mathematics meets YouTube excellence. Welcome to this video where we'll prove a beautiful inequality involving fractions. We'll prove that for all positive numbers, a, b, and c, the following inequality holds. 1 is less than the sum of a over a plus b over b plus c over a plus c, and this sum is less than 2. This is quite an elegant result, and we'll prove both the lower bound and the upper bound step by step. Let's begin our proof by breaking it into two parts. First, we'll prove the lower bound, showing that the sum is greater than 1. Then, we'll prove the upper bound, showing that the sum is less than 2. Let's look at our inequality again. Let's start by proving the lower bound. We'll compare our sum with the fractions having the same numerators, but with a larger common denominator. Since b plus c is less than a plus b plus c, we know that a fraction with denominator b plus c is greater than a fraction with the same numerator, but denominator a plus b plus c. So we can say that b over b plus c is greater than b over a plus b plus c. Similarly, c over c plus is greater than c over a plus b plus c. And a over a plus b is greater than a over a plus b plus c. When we add these three inequalities, we get our sum is greater than the fraction a plus b plus c over a plus b plus c, which equals 1. So we've proven the lower bound of our inequality. The sum is greater than 1. Light bulb tip. Notice how we made the fractions comparable by finding a common denominator. Now, let's prove the upper bound. We'll use a clever approach by rewriting each fraction in terms of its complement. We can rewrite a over a plus b as 1 minus b over a plus b. Similarly, b over b plus c equals 1 minus c over b plus c. And c over c plus equals 1 minus I over c plus a. When we add these three equations, we get our sum equals 3 minus the sum of b over plus b, plus c over b plus c, plus a over c plus a. But we just proved in step 1 that this new sum is greater than 1. Therefore, our original sum is less than 3 minus 1, which equals 2. Thinking face quick challenge. Can you see how we used the result from step 1 to complete step 2? Combining our results from steps 1 and 2, we have proven that 1 is less than the sum of a over a plus b over b plus c over a plus c. And this sum is less than 2. And remember, this inequality holds for all positive values of a, b, and c. This proof illustrates a powerful technique in mathematical inequalities. 1. We broke down a complex inequality into two simpler parts. 2. We use comparison with common denominators for the lower bound 3. We cleverly used fraction complements for the upper bound 4. We reused the result from step 1 to complete step 2. Party popper, congratulations on understanding this elegant proof. Welcome to this mathematical proof video. Today, we'll be proving an inequality for a special sum involving fractions. We want to prove that for every integer n greater than or equal to 1, the sum 1 plus 1/2 plus 1/3 plus, and so on, up to 1 over 2 to the power of n minus 1, is bounded between n over 2 and n. To prove this, we need to use a clever approach by grouping the terms in our sum into specific blocks. Let's start by rewriting the sum in a specific pattern. We'll partition our sum into n blocks, where the mth block contains the reciprocals from 2 to the power of m minus 1 plus 1, up to 2 to the power of m minus 1. For example, the first block is just 1, the second block contains 1/2, the third block contains 1/3 and 1/4, the fourth block contains 1/5 through 1/8, and so on. Now, let's establish a lower bound for each block. We want to show that each block has a sum greater than 1/2. For the mth block, we have 2 to the power of m minus 1 terms, and each term is greater than 1 over 2 to the power of m minus 1. Multiplying these, we get that the sum of terms in the block is greater than 1/2. Since we have n blocks in total, and each block contributes more than 1/2 to the sum, the entire sum is greater than n over 2. Next, we need to establish an upper bound for each block. Let's show that each block has a sum less than 1. For the mth block, every term is less than 1 over 2 to the power of m minus 1 plus 1. Since there are 2 to the power of m minus 1 terms in the block, the sum is less than 1. With n blocks, and each block contributing less than 1 to the sum, the entire sum is less than n. Combining our results from steps 2 and 3, we've proven that the sum 1 plus 1/2 plus 1/3 plus, and so on up to 1 over 2 to the power of n minus 1, is strictly greater than n over 2 and strictly less than n. This gives us our desired inequality. Welcome to our math tutorial. Today, we'll be proving a mathematical inequality step by step, following the exact solution process shown in our problem. Let's start with our problem. We need to prove the following inequality. A over b plus b over c plus c over a is less than b over a plus c over b plus or over c, where a, b, c are positive real numbers, and is greater than b is greater than c is greater than 0. Let's follow the first step in our solution process. We'll first rewrite the inequality by moving all terms to one side, making it less than 0. In the second step, we'll find the least common denominator for all the terms. We'll combine all these terms over a, b, c. In the third step, we'll rearrange the terms in the numerator and notice something interesting. We can regroup these terms. In the fourth step, we'll continue factoring the expression. Notice that we can factor out common terms from both groups we created in the previous step. In the fifth step, we'll factor out the common expression from the numerator. We can see that the expression ab minus ac minus b squared plus bc appears in both terms. In the sixth step, we'll further factor the second part of the expression. We can take out a factor of b minus c from ab minus ac minus b squared plus bc. In the final step, we'll analyze the sign of this expression based on our given conditions. Remember, we're told that a is greater than b is greater than c is greater than 0. Let's analyze each factor. Since c is less than a, c minus a is negative. Since a is greater than b, a minus b is positive. Since b is greater than c, b minus c is positive. And since a, b, and c are all positive, abc in the denominator is positive. Therefore, we have a negative times a positive divided by a positive, which results in a negative number. This confirms that the expression is less than 0, proving our original inequality. Welcome to this tutorial on proving inequalities. Today we're going to work through an interesting inequality problem involving 3 variables x, y, and z. Let's start by looking at our inequality. We need to prove that x squared times quantity z squared minus x squared times quantity x squared minus y squared plus y squared times quantity x squared minus y squared times quantity y squared minus z squared plus z squared times quantity y squared minus z squared times quantity z squared minus x squared is less than or equal to 0, where x, y, and z are real numbers. Since the inequality is symmetric with respect to all variables, we can assume without loss of generality that x squared is greater than or equal to y squared, which is greater than or equal to z squared. Based on our assumption, let's see what we can determine about each term in our inequality. First, we know that x squared minus y squared is greater than or equal to 0. Similarly, y squared minus z squared is greater than or equal to 0. And finally, z squared minus x squared is less than or equal to 0. Now let's analyze the third term in our original inequality. This term contains z squared times quantity y squared minus z squared times quantity z squared minus x squared. Based on our implications, y squared minus z squared is greater than or equal to 0, while z squared minus x squared is less than or equal to 0. So the third term is less than or equal to 0. Now, let's look at the first 2 terms of our inequality. We can rewrite them as follows. By factoring out x squared minus y squared, we get quantity x squared minus y squared times x squared times z squared minus x to the 4th plus y squared times quantity y squared minus z squared. Further simplifying, we get x squared minus y squared times x squared times z squared minus x to the 4th plus y to the 4th minus y squared times z squared. After rearranging, we get x squared minus y squared times z squared times x squared minus y squared minus x squared plus y squared times quantity x squared plus y squared. This can be simplified to x squared minus y squared squared times z squared minus x squared minus y squared. Now, let's analyze this expression. We have x squared minus y squared squared, which is greater than or equal to 0, and z squared minus quantity x squared plus y squared. But given our assumption that x squared is greater than or equal to y squared, which is greater than or equal to z squared, we know that z squared minus quantity x squared plus y squared must be less than or equal to 0. Therefore, the first 2 terms combined are less than or equal to 0. Now we can combine our results. We've shown that the first two terms together are less than or equal to 0, and the third term is also less than or equal to 0. Therefore, the entire left-hand side of the inequality is less than or equal to 0, which proves the original inequality. Welcome to our math video lesson. Today, we're going to prove an interesting inequality involving variables a and b, where both are positive real numbers. Let's work through this step by step. Here's our inequality problem. We need to prove that a cube times quantity b plus 1 plus b cubed times quantity a plus 1 is greater than or equal to a square times quantity b plus b squared times quantity a plus a squared, where a and b are both positive. Let's start by moving all terms to the left side of the inequality. We'll rearrange to get a 3b plus a 3 plus b3 a plus b3 minus a squared b minus a squared b squared minus b squared a minus b squared a squared is greater than or equal to 0. Now, let's distribute and expand the terms. We get a cube b plus a cube plus b cubed, a plus b cubed minus a squared b minus a squared b squared minus b squared a minus b squared a squared is greater than or equal to 0. In this step, let's group similar terms together. We can rearrange as a cubed b minus 2 a squared b squared plus b cubed a plus a cubed minus a squared b plus b cubed minus b squared a. This is greater than or equal to 0. Let's factor out common terms in this step. We can factor out ab from the first parenthesis, a squared from the second parenthesis, and b squared from the third parenthesis. This gives us ab times quantity a squared minus 2ab plus b squared plus a squared times quantity a minus b plus b squared times quantity b minus a. This is greater than or equal to 0. Now, let's recognize the pattern a squared minus 2ab plus b squared as the perfect square of a minus b. This gives us ab times quantity a minus b squared plus a squared times quantity a minus b squared times quantity a minus b is greater than or equal to 0. Let's factor out the common factor a minus b. This gives us a minus b times quantity, ab times quantity a minus b plus a squared minus b squared is greater than or equal to 0. Let's further simplify the expression inside the square brackets. We know that a squared minus b squared can be factored as quantity a minus b times quantity a plus b. So our expression becomes a minus b times quantity a minus b times a b plus quantity a plus b times quantity a minus b. This simplifies to a minus b times quantity a minus b times quantity a b plus a plus b. For our final step, let's simplify further. We can rewrite this as quantity a minus b squared times quantity a b plus a plus b is greater than or equal to 0. Now, let's analyze the sign of each factor to determine if the inequality is always true. First, we know that quantity a minus b squared is always non-negative for any real values of a and b. Second, since a and b are both positive, ab is positive, and a plus b is positive, so ab plus a plus b is always positive. Therefore, the product quantity a minus b squared times quantity a b plus a plus b is always greater than or equal to 0, which proves our inequality. Therefore, the original inequality is always true for positive values of a and b. We've successfully proven that a cube times quantity b plus 1 plus b cubed times quantity a plus 1 is greater than or equal to a squared times quantity b plus b squared times quantity a plus a squared for all positive values of a and b. Welcome to our math tutorial. Today we're going to solve a mathematical proof step by step. Let's start by understanding the problem. We're given several conditions and need to prove the inequality p, r minus q squared, is less than or equal to 0. We'll solve this using proof by contradiction. Let's start by assuming the opposite of what we want to prove. Let's assume that p, r minus q squared is greater than 0. From our original conditions, we know that ac minus b squared is greater than 0. We can combine this with our contradiction assumption to derive a new inequality. Now, let's work with one of our original equations. ap minus 2bq plus c, r equals 0. First, we'll rearrange it to ap plus c, r equals 2bq. Next, we square both sides of this equation. This gives us ap plus c, r squared equals 2bq squared. Let's expand this squared expression. We get a squared p squared plus c squared, our expression. We get a squared p squared plus c squared, r squared plus 2apc, r equals 4b squared q squared. Now we'll use our previous results labeled as I and 2 to derive a contradiction. From I, we know that AP, our C, is greater than B squared, Q squared. From 2, we have a squared P squared plus C squared. Our squared plus 2AP, our C equals 4B squared, Q squared. Continuing with our simplification, we subtract 2AP, our C, from both sides of the inequality. This gives us a squared P squared plus C squared. Our squared minus 2AP, our C is less than 0. We can factorize this expression. Notice that this is the square of a difference. AP minus C, our squared, is less than 0. But here we have a problem. A square of any real number can never be negative. So we've reached a contradiction. Therefore, our initial assumption must be false. So PR minus Q squared is less than or equal to 0 must be true. This completes our proof. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.